Hello fellow problem solvers! So today we're doing a problem from Korea. Final round from the year 2001, problem number 1. Actually, South Korea. So I suggest you try this nice functional equation problem out. It's it's not a lot of big ideas. It's really meant to help you technically with number theory and functional equations for a minimum of 20 minutes, ideally an hour-ish, not more than 2 hours. If you'd like to go along with us, give this a go for the next 5 minutes. And now let us begin. So, what's up with this function? We have an odd prime p, okay, that's a bit odd. And we must find a function that f of m is f of n for every, so if two numbers are the same modulo p, then their f's are the same. That's what the first condition is saying. And the second one says it's multiplicative. Okay, so let's think about this. Well, we have that with multiplicative functions immediately. We have f of 0. If I just plug in f of m is equal to 0 is equal to f of 0 times f of n. Now, if f of 0 was equal to, what's it called, 1? Like here you have a couple of options. Either f of 0 is equal to 1, in which case f of n is equal to 1. So for every n, f is equal to 1. Satisfies the conditions of our problem, or f of 0 is equal to 0. And then we're going to find another type of function. Now if we plug in a 1, we're going to have f of 1, and we're only plugging in it here, is going to be equal to, actually f of n is going to be equal to f of n times f of 1. And now you have one of two options, either that f of n is equal to 0 for all n, right? That's option number 1. Or if there's a non-zero n, then say if there exists an n that's not such that f of n is not equal to 0, then we have f of 1 is equal to 1 from here. Because then we can divide through. So we already have a couple of solutions, right? One is f is identically 1, f is identically 0. Those are our first two solutions. And in all these other solutions, we're going to have that f of 1 is equal to 1, and f of 0 is equal to 0. Okay, that sounds pretty fine, nice and dandy. So now what do we do with this? What does this mean? If f of 0 is 0, pause for maybe 5-10 minutes and try to push the problem further here. Now what happens if f of 0 is 0? F of 0 is 0 means that every number that's divisible by p is also going to be 0. F of 1 is 1. Every number that gives a remainder of 1 when divided by p is also going to be congruent to 1, right? So that's what these two are now implying. Like if we really catch just the first p values from 0 to p minus 1, we have the entire function figured out. So really what this thing over here is telling us, yeah, sure, it's multiplicative, but just look at the numbers which are the residues. We just care about the residues here in this whole multiplicative thing that we're talking about. We care about mn modulo p is m modulo p times n modulo p, like f. So what are we going to do now? Well, we have things which are congruent to 1. So let's say we have some m that is not divisible by p, and we're looking at what can f of m be congruent? What can it be equal to? Okay, pause for 2-3 minutes and think about what are the possibilities for this. And if you think about it, well, for m, there's a q, there's an x, such that m times x is congruent to 1 modulo p, right? Why does such an x exist? Well, it's because m times 2, m times 3, all the way till m times p minus 1. None of these are 0 modulo p. P does not divide m. And if two were congruent to each other, then we'd have m times I minus j, for the I and j that are congruent to each other, would be divisible by p. This is relatively prime, and if p divides I minus j, I and j are between 1 and p minus 1. That's an impossibility. So this goes through all the residues. And so for one of them, we're going to hit a 1. That's the proof. And with this, you have m times x is 1. So we have f of m times f of x is equal to f of mx, which is the same as f of 1, which is f of 1. And f of 1 is equal to 1. So f of m is going to be equal to either 1 or minus 1 for every single m. And here I'm going to invite you, so like from here we have f of m, because mind you, we are from the integers to the integers. F of m is an element of minus 1 and 1 for every single m. Here I invite you to pause for about 10ish minutes and try to push the problem further yourself. And here is the next step after I clear everything up and write down what it is we've had so far. And what we have when we clear everything up is this thus far. We have our solutions. F is identically 1, F is identically 0, and now we have to think about all these other solutions. This is for P that does not divide M. Okay, so now what? What are we to do next? Well, okay, if all the M's, if all of them were equal to 1, that would be a solution, right? Then we can just check that out. All are 1, we're good. So let's assume like that. I mean, that's a separate solution. So f of x is equal to 0 for all p divide x, and f of x is equal to 1 for all p that don't divide x. So this is our third solution, second solution, first solution, right? So this is one way that we can figure this function. So let's assume there exists an m such that f of m is equal to minus 1. And now things are getting spicy, aren't they? They're going to get a lot more interesting now. So let's think more about the problem. So you're going to have a minus 1. Can we also, okay, we're playing around. We have this multiplication stuff going on. Well, also with the multiplication I have, if I just plug in m is equal to n, I have f of n squared is the same as f of n squared. And this f of n is either 1 or minus 1, so f of n times f of n is going to be equal to 1. So every number that's a quadratic residue is going to be equal to 1. Like, this is important. This is also the thing that holds true always. If R is quad residue, then we have f of R is equal to 1. Okay. So this m that's equal to negative 1, that can only be a quadratic non-residue, a non-quadratic residue. I don't know what the correct terminology is. So this is the type of m we could have. Now here I would invite you, perhaps, if you didn't come this far, pause for another 5 minutes and try to push the problem along, push it further. And what are we going to have now? Okay, we have this m. Let's just plug it in here and see what we have. We have then f of n times m for any n is going to be equal to minus f of n. Okay? So what does this mean for us? Well, we know that we have, how many quadratic residues do we have? Well, these are numbers. 0 squared, 1 squared, all the way till p minus 1 over 2 squared. So if we forget about the 0, these are 1 through p minus 1 over 2. So if, like, the 0 one is a special one, right? Special quadratic residue, and we already have that one handled, right? So we're going to have p minus 1 quadratic residues, p minus 1 over 2 quadratic residues, quad residues, and then p minus 1 over 2 of them are now going to be quadratic residues. And why is also this? If 2 of them were congruent, if we had some I squared is congruent to j squared, modulo p, this would mean p divides the difference of these squares. In other words, p divides I minus j times I plus j. But I plus j is at most p minus 1 over 2 times 2, so p minus 1. And it's at least 1 plus 1, which is 2. So this only happens if I is equal to j. with I and j that are here. And if you add anything else, if you had like p plus 1 over 2 squared, well, that's the same as this. They sum up to p. So that's why you have p plus p minus 1 over 2 quadratic residues, and then p minus 1 over 2 quadratic non-residues. So if n is a quadratic, so m is a quadratic non-residue, right? That's what it has to be if such an m exists. Now the question is, if I'm taking n that goes through all these quadratic residues, am I ever, and then this is going to be minus 1, am I ever going to, does that go over all the quadratic non-residues? So for n is 1, I get m, we already have n. For n is 2 squared, is this going to go over all of them? And now we're going to check that. So if the quadratic residues are r1, r2 till rp minus 1 over 2, then we're looking to see is our mr1, mr2, and so on and so forth till mrp minus 1 over 2. Are these numbers, can they be equal to one of these? Right? Can they be quadratic residues as well? And you can also look at these as 1 squared, 2 squared, so on and so forth. So now, and m is such that there isn't a square that's a quadratic residue. Now, how do we deal with this? Please, this is the setup. Pause for 10 minutes. Let me clear the board up, and then let us get back into our problem. So here's the board cleared up. And now that I've cleared up the board, what we have is, can this be the case? Can m times x squared be congruent to some y squared modulo p? Like here, this is equivalent to this. These are the quadratic residues. Quadratic means there exists an x, there exists a y. Can some of these, go into another quadratic residue? And that would be equivalent to this. Now, it doesn't look, why can't this happen? Why not? This sounds perfectly plausible. What's wrong with it? The thing that's wrong with it, well, just as m, so does every number has a inverse. It's called an inverse modulo p. For an x, there exists a z such that x times z is congruent to 1 modulo p. So if I multiply both sides by z squared, I'm going to have m times xz squared is congruent to yz squared modulo p. And thus this is 1, so I'm going to have m is congruent to yz squared modulo p. In other words, then m is a quadratic residue. That's a contradiction. I said m is not a quadratic residue. And then the second thing to check is, can two of these give us the same non-quadratic residue? So all of these give us non-quadratic residues. So can the two of them give us the same one? Well, let's see if mx squared is congruent to my squared for y and x, which are different, modulo p. That means p divides m times x squared minus y squared. And you've probably gotten used to this by now. M and p are relatively prime, so this cancels out. X minus y times x plus y. Well, x and y, x plus y, is here the x and y's are between 1 and p minus 1 over 2. So this x minus y is at least 1. And if x is bigger than y, without loss in generality, this is at least 1. And this x plus y is at most p minus 1 over 2 plus p minus 1 over 2. In other words, p minus 1. So close. So p does not divide this, and so there do not exist x and y such that this is the case. In other words, these numbers, once I multiply m with all the quadratic residues, I'm going to get all the quadratic non-residues. So these are I don't know how to label them, say. This is going to be kind of silly, but maybe r1 prime, r2 prime, all the way till rp minus 1 over 2 prime. So n times m, if n goes from r1 to rp minus 1 over 2, I'm going to get all these quadratic non-residues, and here I'm going to get quadratic residues, which are equal to, f of that is equal to 1, as we've seen before. So the f of the quadratic non-residues is going to be -1. And that finishes the problem. Like, that's what the function is. So those are our 4 solutions. F of x. So f is identically 0. This is f1. F is identically 1. F is, what's it called? 0 for all numbers that are divisible by p. And f is 1 for all numbers which are not divisible by p. And what's it called? This is f of x. F of x. This is the 3rd function. And the 4th function is really f of x is, I think this is the notation. This is called Lagrange functional equation. But really, +1 if it's a quadratic residue, -1 if it's not. If it's divisible by p, then it's a 0. And that's it. Those are the solutions. We can plug them in, check that they work. These 3 are pretty straightforward to check that they work. Here, like, the only thing that we need to check out is the multiplicative function. Like, we've defined them with regards to, like, their remainders modulo m, so we don't have to check that. And what's it called? This one, we just need to check that if I multiply 2 quadratic residues, then I'm going to get a quadratic residue. So if m and n are some quadratic residues, I'm going to have, is x squared plus times y squared a quadratic residue? Yes, it is. If both are quadratic non-residues, when I multiply them together, am I going to get a quadratic residue? Now that would be a thing we need to prove, that if I have 2 quadratic non-residues, when I multiply them together, I get a quadratic residue. And I'm thinking of the easiest way to go ahead and prove that is, okay, so these are quadratic non-residues. I'm going to pick one of them, say m is one of them, and then I do the same thing before. I multiply m with every single one of these, and I show that they form a complete set of quadratic residues. I think that is good enough. So no 2 are the same, but can one that's not a quadratic residue go into another one that's not a quadratic residue? How would I prove that? Actually, let me pause. You can pause for 5-10 minutes and try to prove that, and I'll clear up the board. And what I've done here is, okay, I need to prove that if I do a product of that, why will I not get a quadratic non-residue? And the answer is, well, what I'm doing when I'm multiplying m, I've already proved that if I multiply a quadratic non-residue with a quadratic residue, I'll get a what? A quadratic non-residue. So if it was like when I'm multiplying m with these numbers and these numbers, I'm effectively and not 0, I'm effectively multiplying m with numbers 1 through p minus 1. Right? These are all the possible residues outside of 0. So by the previous thing, if I'm multiplying m with all of these, no 2 can give me the same remainder. So if I multiply m with the quadratic residues and they give me the non-residues, when I multiply them with the quadratic non-residues, they have to give me these residues. P minus 1 is here. They've taken all the p minus 1 over to non-residues here. So all of these have to take all of these. And that is why this function works out. So with that in mind, okay, that's when I multiply a non-residue with a non-residue, I get a residue. Or not a non-quadratic with non-quadratic, I get a quadratic. I proved that if I multiply a non-quadratic with a quadratic, I'll get a non-quadratic, which is identical. And when I multiply 2 quadratics, I'll still get a quadratic. So that is all I need to prove. And that finishes up our problem to prove that this function actually works. Now this is it. Our problem is done. A beautiful little, technical problem. And as always, thanks for problem solving.